So we need to take the mass of water and divide by the molar mass to get the number of moles of water. It says 15, we got 4 sig figs there, 8269 moles. And then we need the moles of ethylene glycol. So we've got 55.3 grams. And let's see, 1, 2, 3 carbons times 12.01 plus 2 oxygens times 16 plus 2, 4, 6, 8 hydrogens. 8 times 1.008. 76.094. Anybody else get that molar mass? Thanks. 55.3 divided by 76.094. So we've got 0.72673 moles of that. So we'll plug the number of moles into our equation for the mole fraction. And then in the bottom we have the sum of the two. Plus 0.72673. The denominator, we're still going to have 4 sig figs, so we don't need to worry about that. So we have 15.8269 divided by the quantity 15.8269 plus 0.72673. Get a mole fraction of 0.956098. And that has no units. So this mole fraction then comes up into Raoult's law, where it's the mole fraction of the solvent, that's what we calculated, times the vapor pressure of the pure solvent. Vapor pressure of the pure solvent is 23.8 torr. So the vapor pressure of this solution is 22, it should have 3 significant figures, 22.8 torr. The vapor pressure of the water is lower because there's ethylene glycol in it. Any questions? What if we have a volatile but non-electrolyte solute? When the solute is volatile, it contributes to the vapor pressure. Remember, a volatile substance is one that evaporates easily. So now we've got the vapor pressure of the solvent, and we also have a vapor pressure from the solute. So this makes things a little more complicated. When things are, when we have an ideal solution, that will follow Raoult's law at all concentrations for both the solvent and the solute. And here things are fairly simple. The total pressure above an ideal solution is just the sum of the partial pressures of the components. Of course, you think ideal solutions are normal? No, probably not. Nothing's ever ideal, is it? We encounter non-ideal solutions quite frequently. Non-ideal solutions don't follow Raoult's law because of interactions between the solute and the solvent molecules. If those interactions are extra, particularly strong or particularly weak, then things become a little different. So let's look at this. So in this graph, we have vapor pressure increasing on the y-axis, and we have the mole fraction of component A increasing as we go across to the right. So if we look at the partial pressure of component A, where its mole fraction is 0, its vapor pressure is 0. And as it increases linearly until we get to its pure vapor pressure at a mole fraction of 1. The vapor pressure of B is in blue, the partial pressure. When the mole fraction of A is 0, the mole fraction of B is 1. And so its vapor pressure is equal to the pure vapor pressure. And it decreases linearly to 0. For a mixture, you just add the two vapor pressures, and we also get a straight line. That's an ideal solution. If we have strong interactions between the solute and the solvent, do strong interactions within the solution cause higher vapor pressure or lower vapor pressure? Lower vapor pressure, right? It's harder for the molecules to break free. So when there are strong interactions between the solute and the solvent, then we see a bowing in these lines, and it goes below what is expected. So the vapor pressure of component A is lower than expected, except where the mole fraction is 1 and the mole fraction is 0. Because at that point you have a pure substance, either A or B, and there's no interactions. And for component B, we also see this dip. And so the vapor pressure for the total solution is still the sum of the two individual pressures. But here we see a deviation. Raoult's law predicts this straight line, and it dips significantly below that. And the maximum effect is where you have roughly equal molar quantities of the solute and the solvent. If we have especially weak solute-solvent interactions, you can almost think of them like wanting to get away from each other, right? The solute and the solvent are like not mixing up very well. And so they're like, I really want to escape into the gas state. It's better out there. I can get away from you, right? And so we see an increase in vapor pressure for each component. And then when we add those together, we get this higher than expected vapor pressure for the solution. Does that make sense? We're not going to do calculations with that, thankfully, but we need to be aware of the phenomenon. Let's look at this. A solution of benzene and toluene is 25% benzene by mass. The vapor pressure of pure benzene and pure toluene at 25 degrees Celsius are 94.2 torr and 28.4 torr, respectively. Assuming ideal behavior, calculate the following. The vapor pressure of each of the solution components in the mixture. So we want to know what's the vapor pressure of the benzene and what's the vapor pressure of the toluene. What equation are we going to use to find that? Raoult's law. So the pressure, I'm going to call benzene Ben. The partial pressure of the benzene will equal the mole fraction of the benzene times the vapor pressure of pure benzene. And likewise for toluene. So we're going to need mole fractions. Well, we've got this 25% benzene by mass. So 25% benzene. That means there's 25 grams per 100 grams, right? So I'm going to say, well, let's just pretend that it weighs 100 grams, then I know I have 25 grams of benzene and I must have 75 grams of toluene. With masses, I can calculate numbers of moles. So I'm going to say we've got 25 grams of benzene, and then we want to find the number of moles of benzene. So I did some of these calculations ahead last night, because this one's a bit of a booger. So we can calculate the molar mass of benzene. I got 78.108. And that gives us a number of moles of 0.32007. That's moles of benzene. Then I must have 28 grams of toluene. I'm going to call him tol. We calculate the molar mass of toluene. Correct me if you find any mistakes. I got 92.134 grams per mole. And doing the math there, I get a number of moles of 0.81403 moles of toluene. So now we need mole fraction of benzene. The mole fraction of benzene, chi ben, is going to equal the moles of benzene, 0.32007 moles, divided by the total number of moles, 0.32007, plus the 0.81403 moles. And that comes out to be 0.28222. That's the mole fraction for benzene. So then to find the partial pressure of the benzene, we take the mole fraction, 0.28222, and multiply by the vapor pressure of pure benzene, which is right here, 94.2 torr. So that comes out to be 26.585 torr. So that's one answer, vapor pressure of each solution. I'm not going to round that yet because we're going to need that for the next part. If you were just reporting that one, you'd say 26.6 torr. Any questions? If this is the mole fraction of benzene, what's the mole fraction of toluene?